Thanks to you all for coming. And mostly thanks to Andrea, who's not here today, Massimo, Francesco, for the invitation. I work at the Spanish Open University, which is UNED in Madrid. But now I'm visiting here for a few weeks in the Instituto Europeo de Oncología. So for me, this is mostly an opportunity to meet the Milanese philosophical community. And for this alone, I'm very grateful. So I'm mostly a philosopher of the social sciences and medicine that for the last few years I've been working on the problem of biases in experiments with humans in both the biomedical and the social sciences. So the biases that experimental subjects and the experimenters introduce in the tests. And I've been studying the debiasing methods, the methods that we use to correct those errors, and how do we justify them epistemically. So, I mean, the outcome of this research project I've been involved in is an epistemic justification of these debiasing procedures in a contractarian way. And this is going to be my claim for this audience, that contractarian epistemology gives the best possible justification for debiasing methods. But this might sound too abstract, and this will be just the end of my talk. I'm going to get the step-by-step introducing my claims very slowly. So if at any point you are lost, please interrupt me, and if you don't get what I'm saying in English, just interrupt me as well, because I'm very aware that my English is far from perfect, and I do have an accent. So, you might have another accent, but mine is sometimes thick and difficult to follow for some. So okay, so I start with a few slides of motivation, motivating my claim that we should care about biases in experiments. And luckily for me, The Economist came to help me only this last Monday, publishing a very interesting report on how scientists are cheating in the most diverse fields. And this is making science goes wrong. So the obvious answer to the question, why are debiasing methods important, is because, well, there are very important biases that we should care about. Case in point, conflicts of interests in biomedical research, stereotyping, biased research. So we assume usually that scientists are working for the common good, in the public interest. They are seeking truths, they are caring about patients, and these are shared interests, things that we can adhere to. But it often happens, at least in biomedical research, that scientists deviate from these noble goals. They start seeking their own private interests, such as the financial interests, and they deviate from truth. For instance, the New England Journal of Medicine, one of the best medical journals, an excellent outlet, adopted like a decade ago a very tough policy on conflicts of interests. So if you published pieces on drugs, editorial reviews, I mean, you were supposed to have no connection whatsoever with the manufacturing company. Known means known. Only 2 years, this was changed into a sort of softer statement in which it was required that people had non-significant affiliations with the pharmaceuticals. And as you can see on this slide, this involves owning less than $10,000 in stock. And is this significant? Well, it all depends on your salary, but for these people it seemed insignificant enough. So why this change in only 2 years? I mean, what did they soften the policy to fight conflicts of interest? Well, mostly because they were receiving no submissions, and journals live out of submissions. So basically in this section, they could only publish one single piece. So for biomedical researchers involved in drug testing, it is not publish or perish. I mean, it's publish or lose money. And their choice is clear. I mean, they don't want to lose the money. They can postpone publishing if they have to choose. So this is a sort of intuition of what a conflict of interest is. And conflicts of interests are generated by biases. Now, as a first approximation, let's take a bias to be some sort of cognitive mechanism or psychological mechanisms that make people deviate from truth. This is a very rough first approximation, and given the books I'm seeing on the table, I'm sure that Madeo has taught you a lot more about what biases are. But let's make a division here between conscious and unconscious biases. So conscious biases runs from the conflict of interest, so you have two conflicting goals, runs from these conflicts of interest to scientific fraud. You are cheating and you know it. You don't care. Like in human cloning. These are the conscious variety of bias. We're going to focus on the following slides in the unconscious biases. Those biases that pervade our cognitive operations daily, and we don't know. We're not aware of them biasing us. Case in point, the confirmation bias. This has been defined sometimes as the unwitting selectivity in the use and in the acquisition and use of evidence, which means that we don't give the same weight to the evidence that confirms our prior beliefs than to the evidence that disconfirms these beliefs. So we accept very easily what confirms our prior beliefs. We resist fiercely what somehow puts them in question. So this has been documented in a number of experimental settings, and this is just one to illustrate it. It's a fictitious medical test. So you tell your experimental subjects that they are undergoing a number of medical tests. And the first test requires that they go into a room, they pick one of these strips, they dip it in their mouth, they see if there's a change in color, and then they proceed to the following room. Now we divide our group, this group of subjects, in two, and half of them are given a positive interpretation. So if it changes color, you have, so there are people here that I don't see, so I'm on here, sorry. So if the strip changes color, you have immunity against a very rare condition. And that's in principle good, because you didn't know you had it. But if to the other group, they are told that if the strip changes color, it means that they have a rare disease. So the experiment starts, and people go into the room. The people in the positive group usually get into the room, pick up one of these strips, dip it in their saliva, see it change color, they smile satisfiedly, and they go into the following room as quickly as that. But the people in the negative interpretation group pick one of these strips, dip it in their saliva, see it changes color, they don't like it, they throw it away, they pick another one, they dip it, it changes still, and they spend time. So they redo the test a few times until they are convinced that they have this rare condition, and then they go to the following room. Usually, on average, it takes like 5 more minutes for people in the negative interpretation group to move into the following room than it takes to the people in the positive condition. So what it means is that if you find evidence that confirms what you already think, basically that you're healthy, and you accept it without further complications. If you find evidence showing something that you don't want and you didn't believe, you resist it. You fight, to see the evidence reverse it. And this happens in our daily life. It can happen as well in science. So, and the same experimental setting can illustrate it very well. So, imagine you're a scientist, you want to see your hypothesis confirmed. So, you do your test, and you see positive evidence for your hypothesis. Well, you declare it good. You move to the publication stage. Whereas if you see it disconfirmed, you may feel tempted to redo the test and try to fiddle with the experimental setting in order to see whether there's some sort of salvation for your hypothesis. Has this happened? Well, luckily for us, there is a group of psychologists in Toronto led by Kevin Dunbar who conducted a field study in three molecular biology laboratories in the United States. And what they did there was to attend the laboratory meetings and see the discussion of the results. So you have the figures there. So they followed like 417 results obtained in 165 experiments. Almost half of them were positive, almost half of them were negative regarding the hypotheses they were testing in these labs. So interestingly, initially, 196 of these 200 negative results were declared scientific errors. So there had been a malfunction in the apparatus. This is why the evidence was negative for the hypothesis. Is it really the case, or is it a confirmation bias? Well, fortunately, the laboratory meetings worked like courts of appeal. So some of the experiments were followed up, and some of them were actually replicated, and the number of actual anomalies, in Kuhnian terms, grew dramatically. So 54 of these experiments were replicated, and 84 turned out to be real anomalies. So in a way, and luckily for us, science is self-correcting regarding the confirmation bias. So, taking stock here, what I claim so far is that unconscious biases, such as the confirmation bias, are in operation in our daily life, inside and outside science. I mean, they are pervasive. We all suffer from them. But in science, there are correction mechanisms that keep these biases under control. So what sort of mechanism could this be? Well, ideally, if we wanted to control a bias, we should have some sort of method that identified the cause of the bias, and once it is spotted, you go and fix it, as if it was any other machine. If a machine malfunctions, you find the cause of the malfunction, you fix it, and there it is. And you have corrected your mistake, your error. But the problem with biases, and I'm sure Matteo can go on this at length, is that we don't have a unified theory of them. What we have is a catalog of phenomena documented in all sorts of laboratory settings, for which there are many competing exploratory theories. And I've just listed a few of them here. And not all of them hinge on the motivations of the experimenter. I mean, the preferences that you might have or not. I mean, you can have a confirmation bias even for things you don't care about. I mean, it just happens. So, since we don't have a good, unified, consensual theory of how biases emerge, how do we correct them? Well, usually in scientific laboratories, they are corrected on a case-by-case basis. So one thing that Kevin Dunbar and his team documented in these laboratory meetings was the existence of what they called known standard control conditions. And basically, these were rules of thumb to know whether you were actually dealing with an error or an anomaly. So if you observed like a weird result, something unexpected, before declaring it an error, which is what you're tempted to do because you want to see your hypothesis confirmed, before you declare it an error, what you have to do is to replicate your test with materials you know well, like samples for which you already know the expected outcome. I mean, see if the machine is working properly with samples that you know well, and if it does, then you have an anomaly. If the machine is not working properly with these known control conditions, then you have an error. I mean, this sort of rule of thumb prevents the experimenters to follow their gut feelings about evidence. So before you declare something an error, I mean, test if you have some sort of evidence about your machine working properly. So here comes the first controversial claim. I mean, much to my surprise, because I didn't know it was controversial till I got the paper to the reviewers. And the claim is that biases are experimental errors, just like any other sort of error. Why do I say so? Well, basically because they fall under the standard definition of an experimental error. Basically, they obstruct the measurement process, preventing it from reaching the intended actual value by shifting the result by a magnitude which may be regular or random. So basically, you're conducting an experiment, you want to measure something, if you had no bias, you would find the correct measurement. But since you have a bias, I mean, you deviate from that correct outcome. And this deviation should be corrected, because science is about finding the correct value, of course. And biases in this respect would be one source of experimental errors. There are many others, so malfunctioning machines, uncalibrated apparatus, and whatever. If this is so, if you accept my claim, then debiasing methods would be just error correction methods. I mean, one subtype of error correction methods. Please, Matteo.
You said it's debatable, and I disagree. Because I think it's implicit in the notion of bias something systematic. It is true that we don't have a unified theory behind unconscious or psychological biases, but you don't have a random deviation. You have a deviation in the same direction, and if you collapse bias to errors, I think you might lose the systematic factor.
But errors might be regular, not only random. So.
But before you said you measure...
Oh, no, yeah, sure. No, that's what
Sorry, I missed the regular on the slide.
My fault.
I was talking about the next slide. So, but forgetting about slides, what do you think? There must be a...
There must be a systematic
deviation from...
Absolutely.
something.
Actually, otherwise you wouldn't know.
How do you regard the benchmark from which you measure the deviation then? Question. What's the benchmark starting from which you can detect this deviation that is systematic then?
That's it. Again, this is something that you might only spot on a case-by-case basis, in the sense that, for instance, in this laboratory, it's very unlikely that you have like 50% of errors in your measurements. Okay. There must be some sort of if this was true, this would be a statistical outlier, because in most laboratories, in most fields, the error rate is somehow lower. It can be half. So you have to explain why is it so big. Is it because we really have something exceptional happening here, or is it because we are somehow deviating from the average from a systematic reason? And investigating this deviation, you would find a bias. That's what Dunbar and his collaborators think. But you're right. We always need a benchmark, and the problem I contend is that we don't have a general benchmark. What we have like contextual benchmarks in every experimental setting to find out whether we do really have a bias or something else. Are we...
Okay, now let's go ahead with your hypothesis, but just to make it precise. In the case of psychological biases, you don't have a problem here, because you do have a benchmark, which is a normative theory, either logic or rational expectation, rational choice theory, and so on. So you have a benchmark there from which you can talk about biases in a systematic way, although I agree you don't have a unified brain theory about why it's the unconscious working this way.
But we're in agreement here.
In this case, I keep in back my mind and I keep following your hypothesis to see what you...
But in this respect, we're in agreement. A different thing is how to justify these benchmarks. And that's what we're getting at later on in the presentation. So, but it was my mistake not to be explicit that scientific errors might be regular or random. I just used the random deviation, whereas in the case of psychological bias, Matthew is perfectly right that these are regular. So, what I'm getting at is that the biasing methods, the methods that we use to control for our biases, should be like, are just another kind of error correction methods. And there is a general epistemic problem with these methods. In the words of Alan Franklin, no single one of these methods or a fixed combination of them warranties the validity of an experimental result. And this is the Mickey Mouse version, for those who know, of the experimental's regress argument. So basically, the problem that we have with any error correction method is this. So you have your fictitious medical test. So the one in you get a strip, you dip it in your saliva, and you know whether the strips are working properly. So what do you do? Well, you find a subject who's healthy and whose health has been tested by an independent test. You give him one of these strips and see, whether the strip reveals his true condition. And this would be good as a meta test. I mean, as a test of your test working properly. But how do you know that this meta test is working properly itself? I mean, because maybe this subject you're picking for the meta test is somewhat exceptional, or maybe the strip you're picking here is not entirely like the other strips. So how do you know that the meta test is correct? Well, for this you would need a meta test. And so on and so forth. I mean, you start a sort of regress that Harry Collins called the experimenter's regress. So you are always checking and rechecking and rechecking your experiment to declare it free from errors. So how do you stop this regress? Well, ultimately, you need to rely on someone's subjective judgment. So, I mean, you have to find a skilled experimenter who says, well, look, I mean, I know this setup really well, and I can tell you everything is working properly. And this is somehow subjective. And through this subject, the skilled experimenter, all sorts of social interferences may disrupt, I mean, the confidence that you have in your test. So, this is a threat to the objectivity of experiments. And by the way, The Economist interviewed Harry Collins, and you can find the experimenter's regress in the report last Monday. So he's gaining fame for this. So this is the Harry Collins, like, epistemic conundrum. So taking stock again, just summarizing what I have been contending so far, is that we have no general concept of bias and no general theory about and no general theory of debiasing methods. Rather, what we have is a collection of bias and a collection of debiasing methods grounded on a case-by-case basis. And the problem with these debiasing methods, the epistemic problem, is that since they are justified on a case-by-case basis, they are all prone to incur in the experimenter's regress. So you might object that actually, I mean, it's subjective to declare an experiment free from biases. Is this so? Well, I don't believe this is so. And I'm going to convey now my intuition as to why I don't think this is plausible. And let me get back to medicine, to drug tests, to biomedical conflicts of interest, and think of any clinical trial in which you're testing a new therapy. Now, in principle, in any drug test, there is a constitutive conflict of interest. So people want different things here. So patients want safe treatments, pharmaceuticals want quick access to the market in order to make the most of their patents. So researchers, they want to see in the best possible scenario their theory confirmed, and so on and so forth. I mean, everybody wants different things from the experiment. And once you carry out the experiment, you're going to have winners and losers, because not everybody will get what he or she wants. So patients might not have their favorite drug approved, and the pharmaceuticals might see how their competitors have their drug approved, and researchers might see their competitors as well succeed in the test, and so on and so forth. I mean, there are going to be people who lose this with the outcome of a clinical trial. And the question I want to ask is, how come, if the interests are so big, and the incentives to contest the outcome of the experiment are so tempting, how come everybody seems to accept them? So how come patients, researchers, pharmaceuticals agree on the result of a clinical trial if their incentives and interests are all aligned in the direction of contesting them? So why do drug tests generate consensus? Why do we agree about them? And historically, this is a sort of interesting fact. I mean, debiasing methods, when you introduce them into drug tests, generate bigger consensus. I mean, people tend not to disagree with the outcome of a drug trial when the trial has been properly debiased. I mean, just an illustration, the testing, before the pharmaceuticals, before the big conflicts of interests of today, we get back to the late 18th century and we attend to the test of animal magnetism, therapy, pseudotherapy that became very popular in France in the pre-revolutionary days. And this was an Austrian physician, Mesmer, who claimed that he could cure you by equilibrating your animal fluids, your animal magnetism. And in order to cure you, what he needed to do was to use a wand, sort of magic wand, and I mean, with this wand, he would restore the balance of your magnetic balance. And this was hugely successful, so successful that the guy Mesmer requested the King of France to fund the therapy, so to sponsor him. And what the king did was to create a commission. Okay? What is a king to do? But in this commission, he had people like Benjamin Franklin or Lavoisier, the chemist. And Lavoisier had this beautiful idea of, well, let's see if there is some sort of causal interaction between the therapy and the reaction of the agent. So what he did was to interpose a screen between the mesmerizer and the patient. So he put a screen here, so that the subject could not see whether the therapist was doing something and the other way around. So what Lavoisier concluded was that there was no systematic connection between the reaction of the agent and the manipulations of the physician, because sometimes the agents were mesmerized while nothing was happening on the other side of the screen. And so on and so forth. I mean, you had the mesmerizer there, and the patient was totally ignorant of anything happening to him. So this was the blinded test of animal magnetism. And as you can expect, I mean, the patients revolted because they believed in animal magnetism. And of course, the mesmerizers were equally unsatisfied. But they did not contest the blinding. What they did was to start a sort of cottage industry of blinded replications of the experiment. So, I mean, they wanted to get it right. And they used blinding and in public demonstrations and so on and so forth until the therapy died out, because it was shown conclusively enough that it was not doing anything. So I contend that this is something that generally happens with debiasing procedures. I mean, they create consensus. And mostly for one reason. They provide a warrant of the fairness of an experiment regarding the conflicts of interest at stake. Why? Well, because debiasing procedures prevent people from manipulating the experiment in their interests. So if you blind the mesmerizer and the patient, no matter whether they believe or not in the therapy, I mean, they can't do nothing to interfere in the conduct of the experiment. And even if there is a bias, so if eventually some patients indeed reacted to blinded magnetization, even if there is a bias, it will be a random bias. It won't be in the interest in principle of anyone. So just a random event. So this is my intuition as to why debiasing methods create consensus. So what I want to do now is substantiate this intuition from a more principled perspective, from an epistemic perspective. I can only sketch an outline of my argument here, but you can have it in print in these and other places. If you're interested, I can send these to you, but I'm going to handwave a bit now. So, to convey you what this contradictorian approach is, I ask you to put yourself in the following situation. So we have a group of scientists who are self-interested, so they are seeking their own interest, and they are all competing to see their hypothesis tested and succeed in an experiment. So they want to be declared winners in the race for truth, so to speak. So how do we know, I mean, which of these hypotheses will win? Well, everybody's conducting experiments. And of course, one temptation that you might have in order to promote your own interest is not accepting anybody else's results. So I have an experiment confirming my hypothesis. Well, that's biased. There is an error there. I mean, it was not properly done. But if everybody did this, just to promote, I mean, his own chances, there would be no winner. Because, I mean, there will be no consensus as to what is a correct experiment. And they want to win. I mean, they are in this for whatever. I mean, reputation, fame, money. So, if they want a winner, they need to agree in advance on a set of methodological rules that declare the winner, that establish what a proper scientific experiment is. And if you play by those rules and you conduct your experiment accordingly, you can declare your hypothesis succeed in a sort of legitimate manner. So the question in this setting would be, so what sort of rules, what sort of methodological rules would this community of self-interested people would agree on? And my colleague Jesus Tamura has proved under a number of game theoretic assumptions that one prerequisite for these rules to be accepted is that they should be impartial regarding the conflicting interests at stake. Or in other words, that these rules should give to every hypothesis the same chance of winning or losing in the experiment. And if the rules guarantee this experimental fairness, people, I mean the self-interested scientists, will agree on them and the game of science will sort of start. And this is precisely what I contend that debiasing procedures do. I mean, debiasing procedures guarantee that the testing of the hypothesis will be fair regarding the interests of the various parties that have a stake in the outcome. So if you're testing magnetic therapy, obviously as a patient you might have your preferences. I mean, you might be in favor of magnetism, or you might be a skeptic. And if you're a physician, I mean, you might believe or not believe in the potential of the therapy. What the blinding rule does is to guarantee that the outcome of the test will be independent of all these expectations, of all these conflicting preferences. So it will be fair regarding all these competing interests at stake in the outcome of the experiment. And this can be said for, I mean, a number of debiasing procedures. They all work differently, but they all give the same warrant. Basically, that the test will be fair. Now, what about the experimental's regress? That, as you might recall, I mean, was like the complicated epistemic point at stake in this argument. Well, I contend that this contractorian approach solves the experimental's regress because the agreement is not on the outcome. It's on the procedure. So the experimental's regress is about the outcome. How can you declare that your experimental result is free from biases? Well, you need to check and recheck and re-recheck and re-re-re-recheck, and that's the regress. Yeah, but we are not discussing whether the experiment is free from biases or not. What we are discussing is whether the procedure, the experimental procedure, is in principle free from biases or not. If it is neutral regarding the interests at stake. And this can be proven independently of the outcome. If you randomize treatments, for instance, as in a clinical trial, you allocate treatments to patients at random, there is no way for the allocator to cheat because he cannot control the allocation. I mean, it's a lottery. So in as much as the lottery gives equal probability to every patient to receive the treatment, I mean, there is no possible manipulation of the procedure. And this is not something that needs to be rechecked and re-rechecked and re-re-rechecked. I mean, this can be agreed objectively. And we admit, though, that the outcome might be biased, nonetheless. So imagine you randomize and you find that half of your patients is, in one group are women and the other half are men. I mean, so this is a random event, and it is an obvious bias, but it happened at random. Well, true. I mean, biases might creep in despite implementing a debiasing method. But the interesting point is that if you agree to debias your experiments and be consistent in the use of a debiasing method, the likelihood of these biases recurring in further replications of the experiment decreases. So you make the true outcome more likely to emerge than if you didn't implement such debiasing procedures. So this is why I contend intuitively, because as I'm saying, I'm hand-waving, that the contractorian approach solves the experimental's regress. So, 2 claims so far. There's just one third claim and I'm done. So we have debiasing procedure generating consensus in scientific experiments. And this is, I contend, a historical fact. And on the other hand, I have presented a sort of principled argument, an abstract argument, saying that the reason why this happens is because the experiments are fair, and are fair in this contractorian sense. They were until the impartiality of the test regarding the interests in conflict. So this is a second claim. So how my first and the second claim come together? Because one is history, the other is game theory, so to speak. Well, I found at least a trace of a connection in a scientific experiment. So this is a bit circular, but I think it's somehow compelling nonetheless. So, I'm going to quickly present an experiment on fair distribution processes. So there is a literature on how to distribute costs and benefits, how to distribute wins and losses. Because this can be done in a number of manners, and one crucial result in this literature is that there is a correlation between the fairness of the procedure and the disposition to accept it. So, if a procedure looks fair to you, it is more likely that you will accept an adverse result, costs, losses, whatever, than if you think that the procedure is unfair. I mean, if you perceive that you're paying a penalty as a result of an unfair procedure, you will probably contest the distribution. And I think that scientific experiments distribute wins and losses in precisely this sense. So this is a caption from an experiment conducted by a group of economists on fair procedures. So basically this is an ultimatum game in which there were three. So an ultimatum game is a game in which you divide an amount of money, and this is the proposer, and you, the responder, can only do two things: to accept it or to reject it. So there are three divisions of this amount of money. One very favorable for the proposer, one very favorable for the responder, and one which is sort of egalitarian. They both get the same amount of money. But the beauty of this experiment is that we chose which of these three conditions we present to the subject at random with three different probability allocations. So in one probability allocation, it was very likely that the proposer got the biggest share. In another one, it was very likely that we got like an egalitarian distribution, and in a third one, there was an equal likelihood of getting the three of them. So we informed the subject of which probability allocation he was getting, and we studied the reaction. And the interesting fact that Bolton and his co-authors observed is that people were equally willing to accept adverse outcomes with an equal probability of obtaining them than egalitarian outcomes with a very high probability of getting them. Or in other words, they were willing to trade the fairness of the outcome for the fairness of the procedure. So they were willing to lose if they perceived that the lottery was fair and gave everybody the same probability, and they were as willing to do so as they were willing to get, the egalitarian distribution. So why is this evidence for my claim? Well, because this probability distribution in which each of the three alternatives has an equal probability of happening is precisely randomization, a debiasing procedure. Basically, when you randomize, you give every potential outcome an equal chance of happening. And apparently, we're willing to accept randomization as much as we want to get a fair result. So, coming to my conclusion, what I have contended so far is that the biasing procedure generates consensus about experimental outcomes as a sort of historical fact. I contend that this might be explained from a contractorian standpoint in terms of the fairness that they contribute, that these debiasing procedures contribute to the conduct of the experiment. And I contend finally that there is evidence that we actually, as a matter of fact, appreciate this fairness. I mean, as a good enough warrant to accept an outcome. And with this, I conclude. Thanks. Have I abused you so much? No, it's like 40 minutes sharp, more or less.
It was just perfect.
Okay.
Any questions?
So could you follow my very convoluted English?
I think I could, but maybe not.
No, this is what I'm asking then.
Okay. I was fine with that, and
Very
it was
long.
very well organized. I appreciated that. Just a question, which is not something about understanding, but more kind of what have you been doing so far? Have you ever tested the ecological validity of your hypothesis? Do you ever study a specific context, trying to apply your approach to see if it is working in practice, or have you ever tried to improve a specific context to drive the context to get this sort of outcomes?
No, I haven't, because I've been relying so far on
The
evidence
field.
contributed by other people, like field experiments from these guys and economic experiments. Because, I mean, truth to be told, I mean, coming from where I come now, I work in Madrid. I mean, we lack the financial means I mean, to do such a thing. But I'd be willing to. I mean, that's ultimately the proof that you might, the best proof you might have of the validity of these intuitions. I haven't. I have never read anything regarding ecological validity that goes beyond what Dunbar and his colleagues do.
I'm just wondering whether you can go from the descriptive to the normative. So to use your approach as a prescription for improving scientific discovery in a specific context. That's the question.
I mean, the
Maybe it's also your very last aim. I have no idea.
no, actually, actually, this is all part of a debate that has been going on among philosophers of science in this last decade regarding the validity of clinical trials as a as a test, as a drug test. So basically, there are many people around, like John Worrall, Jeremy Howick, and others that contend that we can dispense with randomization, we can dispense with blinding, and we will get just the same outcome. I mean, so we are somehow imposing costs on patients for the sake of, experimental validity that shouldn't be imposed on them, because these methods are not as necessary as we think they are. And I'm contesting that. I'm actually trying to provide a rationale for the use of these methods beyond their objections. And in this respect, I am somehow taking sides with part of the practitioners in this clinical trials community who think that this is an important topic because biases are creeping in all our drug tests. And ultimately, you might make the question of to what extent the biasing methods per se can correct every potential bias that might appear in a clinical trial. And my answer to that is you can't. No matter how much it's a principled answer, but no matter how much you improve your debiasing methods, no matter how many of them you pile up, eventually there is something you can control for, which is the research question. I'm just and this is self-promotion. I'm just presenting my intuitions. I don't know whether this was good enough as an answer. Thanks. Francesco had another question.
Your last comment clarifies quite a lot. So you're arguing against people who argue that randomization and other
Is dispensable.
are unnecessary. So your claim clearly is only that they are necessary, but certainly not sufficient, right? I mean, because the striking
That's
thing
it.
here is that there is nothing about the truth, causal efficacy, and so forth. So you're not claiming that being fair is enough, clearly, because we can get fairness by throwing a coin, basically.
That's
That will
precisely
not
it.
give us any truth or any causal efficacy. We'll just, allocate like the money in the ultimatum game fairly. So sometimes I win, sometimes I lose. I'm not unhappy, but in the end we don't get to know anything really, right?
That's it.
So
No, that's thanks so much for the clarification, because this is indeed what I contend here. I mean, so there has a debate on whether whether our causal methods. I mean, there has been a debate among philosophers of science about, the power of our causal methods to detect truths out there in the world. So, Nancy Cartwright's examples. You want to test a policy intervention to see what's better to alleviate hunger, to transfer money directly to poor people, or to have indirect transfers in which you give them like food or shelter. So what's best? Well, which of these policies? Well, is it enough to conduct a field trial comparing these two policies to find out? So what is the causal power of this field trial method to discern what's happening out there in the world? And there has been a debate on how good these and other tests are at grasping causal structures in the world. So I'm approaching this question from a different angle. What I'm saying is that since there's lots of uncertainty about the causal structures we're grasping, there is always room to contest that the experiment actually captures what we want to capture, that the experiments find the truth about our policies, for instance. So how can we manage this uncertainty in a way that, allows scientific progress, that reconcile our interests and allow us to keep experimenting and getting better at finding the truth? Well, since these are complicated matters in which there are conflicts of interests, we need some sort of warrant that these interests won't interfere in the experiment. And this is what debiasing methods are. But causality and biases go here in sort of orthogonal directions. I contend that this is a necessary thing, a necessary requisite, as you said, to find truth, but it's not nearly enough. If I have convinced you, you will make me feel so happy.
I'm not convinced, but I see you have a good point.
Oh, thanks. I'm almost as happy.
Yeah, you're using game theory to solve a problem that is difficult to solve. This is a nice trick in the third point. I like it a lot. Can I raise another? Can I raise another challenge? A very philosophical, in terms of philosophy of science. I didn't have time to think of that properly, but imagine you manage to get the consensus by fairness. So you succeed in getting fairness through the game theory solution.
Okay.
Okay. Is there consensus on the procedure? It's a question. Is it consensus on the scientific procedure? Providing you get fairness, is the scientific community happy with the procedure, or do we have a problem there as well? So it seems to me that you give for granted that there is a procedure everybody is happy with. Is it a problem for you or not?
Well, actually,
it's a very old problem.
It is a
scientific method.
It is an old one.
Because I think the answer is contextual, once again. It's not general. When Nancy Cartwright talks about randomized trials are not enough, she provides specific context in which we should look at. It's not general, like a Popperian idea of a scientific method or whatever. So does this make any problem for your own theoretical analysis on paper?
No, that's a very nice point. So basically, what I have tried, so basically I've been, the problem with error correction methods, the ones I've been dealing with here, is that they're all contextual, and they can only be justified on a case-by-case basis. So what I have asked myself is is there something they have in common? I mean, is there some sort of general justification for this casuistic procedure? And that's where I defend it as sort of contractual solution. So they all have something in common, which is that they provide fairness. They contribute fairness to our experimental procedure. But now your question is, well, is it enough to have fairness to get everything we want from science? And my answer is no. I mean, that's following the intuition that Francesco just conveyed. But I think it is important enough at this point in time for the reasons that I'm getting to the first slide. The Economist was pointing out in the report, in the sense that so in the old days, so scientific communities were small and they were self-policing communities. So they had methods, but they had methods, but everybody knew how these methods were used because, I mean, they knew each other personally. I mean, the number of relevant scientists in the world in the 50s was a few thousands. So in each discipline, I mean, they could keep an eye on each other, and the fairness of the procedure was sorted out by sort of regular inspection. So they all checked each other out. But now, I mean, according to the estimate of The Economist, there are like several millions of scientists in the world, and I mean, there is no possible way for us to police each other. I mean, just keeping an eye on what we do. So, if we do not want science to collapse out of the temptation of cheating, frauding, and so on and so forth, we need to agree on rules that allow us to work as a community, so that all the good things that we expect from science might still emerge. I mean, that's the sort of intuition that I want to convey. I mean, it's just, why should we register clinical trials? I mean, we'll register